Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. A journey to the Earth's core. Have you ever wondered what lies beneath our feet? Our planet Earth is not just a solid ball of rock. It has distinct layers, each with its unique composition and properties, much like a giant onion. Unlike an onion, however, we can't simply peel back these layers to see what's inside. The immense pressure and scorching temperatures deep within the Earth make direct exploration impossible. But thanks to scientific advancements like seismology, which studies the vibrations of earthquakes, we can virtually dissect our planet and peer into its hidden depths. Unveiling the first layer, the crust. The outermost layer, the familiar ground we walk and build on, is called the crust. It's the thinnest layer, a mere eggshell compared to the rest of the Earth. Continental crust, where mountains rise and continents sprawl, averages around 30 kilometers, 18 miles, thick. Even thinner is the oceanic crust, which floors our oceans at a depth of around 5 to 10 kilometers, 3 to 6 miles. Despite its thinness, the crust punches above its weight in importance. It's the foundation for our continents and ocean basins, holding the rich tapestry of life on its surface. The crust also harbors the mineral deposits and fossil fuels that fuel our civilization. Most importantly, it acts as a giant insulating shield, protecting us from the scorching heat emanating from the Earth's interior. Diving deeper, the fiery mantle. Delving beneath the crust, we encounter the mantle, the Earth's most voluminous layer, accounting for roughly 84% of our planet's volume. Imagine a gigantic, solid, yet squishy sphere, roughly 2,900 kilometers, 1,800 miles, thick. Unlike the brittle crust, the mantle is composed of hot, dense rock, primarily a mix of silicon and magnesium-rich minerals we wouldn't recognize on the surface. The intense heat, ranging from 500 degrees Celsius to a scorching 2,000 degrees Celsius, 932 degrees Fahrenheit to 3,632 degrees Fahrenheit, keeps the lower mantle in a solid state. However, the upper mantle experiences a different story. Here, the combined effects of heat and pressure create a plastic-like zone called the asthenosphere. This layer behaves somewhat like hot asphalt, allowing the rigid rock above, called the lithosphere, which includes the crust and the upper mantle, to move in slow, churning motions. The movement of the asthenosphere is akin to a giant conveyor belt, driving the motion of tectonic plates, the enormous slabs that form Earth's surface. These plates, like pieces of a colossal jigsaw puzzle, float on the asthenosphere, grinding past each other, pushing together, and even pulling apart. It's the movement of these plates that is responsible for phenomena that shape our planet's surface, like continental drift, the majestic rise of mountain ranges, and the destructive power of earthquakes. A molten heart, the outer core. Our descent continues towards the Earth's fiery heart, the core. Unlike the solid mantle above, the core is believed to be a churning sea of molten metal, primarily iron and nickel. Here, the temperature reaches a staggering 2,400 degrees Celsius to a mind-boggling 6,000 degrees Celsius, 4,352 degrees Fahrenheit to 10,832 degrees Fahrenheit. Hot enough to melt any rock we know. But the immense pressure, millions of times greater than at the surface, keeps this molten metal from vaporizing. Imagine the pressure at the bottom of the deepest ocean trench, multiplied by millions. That's the kind of crushing force keeping the outer core in a liquid state. The swirling motion of this outer core, combined with Earth's rotation, is thought to be the engine that generates our planet's magnetic field. This invisible shield protects us from harmful solar radiation and energetic particles that would otherwise bombard the surface, potentially stripping away our atmosphere and hindering the development of life as we know it. The enigma within, the inner core. As we venture deeper towards the Earth's center, the temperature and pressure continue to rise to unimaginable extremes, exceeding the harshest conditions ever created here on the surface. Here, we encounter the enigmatic inner core, a solid ball roughly the size of Mars, nestled within the molten outer core. Unlike the outer core, the inner core is believed to be primarily composed of iron, with a smaller percentage of nickel. Despite the scorching temperatures that would melt any rock we know, scientists theorize the immense pressure exceeding anything found at the surface is enough to force the iron atoms into a tightly packed crystal structure, making the inner core a giant ball of super-solid metal. A crucible of change, the core's influence on Earth. Though hidden from sight, the Earth's core plays a vital role in shaping our planet's past, present, and future. The churning outer core's movement, as mentioned earlier, is believed to be the engine that generates Earth's magnetic field. This invisible shield deflects harmful solar radiation and charged particles from the sun, preventing them from stripping away our atmosphere and bombarding living organisms with harmful radiation. Without this crucial protection, life as we know it wouldn't be possible. Additionally, the heat emanating from the core is thought to be the driving force behind the movement of the tectonic plates in the mantle. As the core loses heat, it creates convection currents that rise and pull the mantle in a slow, churning motion. This movement of tectonic plates is responsible for continental drift, the majestic rise of mountain ranges, the formation of ocean trenches, and even the destructive power of earthquakes and volcanic eruptions. In essence, the core acts like a giant internal furnace, constantly shaping and reshaping the Earth's surface through its influence on the mantle. Unveiling the mysteries. the challenges and intrigue of studying the core. Studying the Earth's core presents a unique challenge for scientists. Unlike anything encountered in examining the crust or mantle, we can analyze rock samples brought to the surface by volcanoes or drilling to understand the composition of the outer layers. However, the core remains stubbornly out of direct reach. Our knowledge about the core's composition and properties comes primarily from studying seismic waves, vibrations that travel through the Earth during earthquakes. By analyzing how these waves travel and bend as they pass through the different layers, scientists can piece together a picture of the core's density and state, solid or liquid. However, the intense heat and pressure at the core's depth make it a constantly evolving and dynamic environment. The sheer scale of the core, coupled with the limitations of our current technology, leaves many aspects still shrouded in mystery. It's a testament to human ingenuity that scientists can glean so much about this hidden realm using indirect methods. But the unanswered questions continue to fuel our fascination with the Earth's fiery heart. A glimpse into the future, exploring the core's secrets. While directly reaching the Earth's core remains a technological hurdle, scientists are constantly chipping away at the unknown. Advancements in seismology are providing ever more detailed pictures of the core's structure and dynamics. Imagine a future where incredibly powerful seismic networks can map the core with unprecedented resolution, revealing subtle variations in density and composition that might hint at hidden processes or structures. Additionally, research into high-pressure and high-temperature materials might one day allow us to create probes capable of withstanding the core's crushing conditions. These robotic explorers could descend into the Earth's depths, sending back invaluable data about the core's composition, temperature variations, and even the potential existence of a solid-liquid boundary within the outer core. Such missions could revolutionize our understanding of Earth's formation and evolution. They might even pave the way for similar explorations of other planets, ushering in a new era of planetary science. The core's connection to the cosmos, a universal story. The Earth's core is not just a unique feature of our home planet. It's believed that most rocky planets in our solar system, and perhaps even beyond, have cores made primarily of iron. These cores are thought to have formed during the violent birth of these celestial bodies, as gravity pulled in denser elements like iron towards the center. Studying the Earth's core, therefore, becomes a window into understanding the formation and evolution of planets throughout the cosmos. By comparing the properties of Earth's core with what we can infer about the cores of other planets through gravitational measurements and astronomical observations, we can gain insights into the building blocks and processes that shaped our solar system and potentially countless others. For example, a strong magnetic field on another planet might suggest a core similar to Earth's, with a churning outer core generating the field. Conversely, a weak or absent magnetic field could indicate a different core composition or structure. Conclusion: Our exploration of the Earth's interior has revealed a hidden world unlike anything on the surface. The layers. From the thin, rocky crust to the fiery, churning core, work in a complex interplay, a symphony of geology unlike any human-made machine. This intricate dance shapes our planet's geology, climate, and even the possibility of life. The Earth is not a static ball of rock. It's a dynamic system, constantly changing and evolving. The core acts as a powerful engine driving change from the inside out, influencing the movement of tectonic plates that sculpt mountains and continents. It also generates the magnetic field that protects us from harmful solar radiation, a crucial factor for the development and continuation of life. As we continue to unravel the mysteries of the Earth's interior, we gain a deeper appreciation for the delicate balance that makes our planet a habitable oasis in the vast expanse of space. This newfound knowledge not only helps us predict and prepare for geological events but also fuels our curiosity about the formation and potential for life on other planets within our solar system and beyond.